So I welcome you, welcome everyone. Please shall we mute ourselves? Shall we please mute ourselves? So we are looking at lipids. I'm going to look at lipids today. Lipids. So we're going to look at what lipids are. The preamble, we need to understand what lipids are. And we need to know the functions that lipids perform in organisms. Then we need to distinguish between or among fats, among phospholipids, and also among so we're going to distinguish between the fats, the phospholipids, the steroids, and also to be able to describe the composition of these molecules, their characteristics, and also their functions. And then we need to understand the structure of triglycerides. And then also need to apply our knowledge of the phospholipids to the formation of the cell membranes. So basically, we're going to talk about an introduction, then functions, fat acids, glycerol, triglycerides, phospholipids, and look at the waxes, the steroids, glycolipids, and the carotenoids. So I'm going to be looking at the various points that we need to understand. So of importance that you need to know is that when we talk about lipids, we are talking about compounds, we are talking about molecules that come about through the condensation reaction that occurs between fat acids and alcohols. So they are esters of fat acids and alcohols. So for lipids to be formed, they are formed through the condensation reaction between fat acids and alcohols. And the bond that is formed is what is called an ester bond. So remember in carbohydrates, we had bonds which are called glycosidic bonds. In proteins, we have bonds which are called peptide bonds. So now in lipids, we have ester bonds. Now some of the examples of lipids are fats, they are waxes, also have fat-soluble vitamins, that is vitamin A, vitamin D, vitamin E, vitamin K. And also have the glycerides, the phospholipids, the carotenoids, and the steroids. So now, when we look at lipids and compare them to okay, so those that are not muting themselves, you are delaying us because I have to pause talking and then I have to mute you. So let's mute ourselves. So when we look at the lipids, unlike the carbohydrates, which we defined due to their functions or according to their, or rather, we defined carbohydrates according to their structures. So we had monosaccharides, disaccharides, oligosaccharides, and polysaccharides. We categorize lipids according to the fact that they are actually soluble in non-polar solvents. So fats or lipids are water insoluble. So in short, they are soluble in they are soluble in non-polar solvents. So for example, you have ether, chloroform, and benzene. So now these have this property because they consist of many or mainly carbon and hydrogen bonds. They exist many of the elements, carbon and hydrogen. And in comparison or in contrast to carbohydrates, which contain a lot of oxygen. Lipids contain very few oxygen containing functional groups. So that's these are the lipids. So the lipids are mainly built from a skeleton, a simple skeleton, which is made of two main kinds of molecules. So we're going to have a fat acid or fat acids and glycerol. Now, glycerol is a polyalcohol. Remember, we said that these are esters of fat acids and alcohols. Lipids are esters or polymers of fat acids and alcohols. So glycerol is a polyalcohol. It consists of three hydroxyl groups, or the OH group. Now, when we look at the fat acid, the fat acid will contain a hydrocarbon long chain with a carboxylic acid functional group at one end. So it contains a hydrocarbon chain with a carboxyl group at another end. Hence, we are saying that many of these lipid molecules are going to consist of a molecule of glycerol, which is a polyalcohol, and three fat acids, which are adjoined to that glycerol. So remember, each glycerol molecule has three hydroxyl groups. Hence, it means that each fat acid is going to react with one of the hydroxyl groups. No wonder many of these lipid molecules are termed as triglycerides or triacylglycerol, because tri means three, so they consist of three fat acids. So when you look at those fat acids that are joined during the formation of the lipids, they do not need to be identical. So they can be different, they can be identical, they can also be different. So there can be different types of fat acids. Functions of lipids include energy storage. Remember, when we talked about carbohydrates, we also talked about energy storage being a function of carbohydrates. However, we find that actually lipids have a higher calorific value. So lipids are able to store a larger amount of energy. Lipids are able to provide a larger amount of energy compared to carbohydrates, because lipids contain a lot of carbon to hydrogen bonds. It contains a lot of carbon hydrogen atoms and less oxygen atoms. So no wonder they have a greater calorific value, or they provide more energy than carbohydrates. And then lipids can also be used in the process of cell recognition or cell signals. So recall also, when we looked at carbohydrates, we said that carbohydrates also have this function. So what happens is that lipids can combine with the carbohydrates and act in cell signaling. So they are important for that. So they are able to allow certain substances to be able to recognize one another. Lipids also can act as a hormone. So they are very important hormones in the body, which are used for regulation of various systems. Lipids can also be used for structural support of the cell membranes. So we have the phospholipids, which are very important components of the cell membrane. And then lipids can also offer heat and electrical insulation. They can offer heat and electrical insulation. So these lipids are able to prevent changes in the temperatures and also to prevent electrical leakages. For example, when we are talking about the brain or the nervous system, we are talking about impulses which are actually electric in nature. So they are They're electronic or electrical in nature. So when I talk about them acting as insulators against heat changes and also electrical insulation, that's what we mean. And then lipids also act in the process of buoyancy. Buoyancy is it's simply the ability to float. Buoyancy simply means floating. I find that there are certain animals, especially in the cold climate. An example could be a whale, the mammal whale, which stores or which has fat under its skin, and the presence of that fat allows it to be able to float or to exhibit buoyancy. And then it's also important for waterproofing. Waterproof. So fats, lipids can act as waterproof molecules or elements. So vertebrates, animals consist of fats or lipids, in other words, which act to proof water out. So water cannot enter in, and it also regulates water coming through the skin into the body. When you look at some birds, such as the duck, there's also lipids stored on their feathers, and this makes it waterproof. Another example is in plants. Plant leaves have cuticles, which are made of wax. So wax is a type of, it's a polymer, a lipid polymer. And that prevents excess loss of water through the process of transpiration. Then lipids can also function for production of metabolic water. Metabolic water. So metabolic water is simply water as a result of metabolism. So lipids, through the process of metabolism, are able to produce water. So for example, in animals that live in adverse conditions where water is scarce, for example, the camel. Camel is able to produce water just from the metabolism of lipids. The other function is that lipids protect the internal organs. So for example, the heart, the kidneys, the spleen, they are able to act as cushions. They're able to act as shock absorbers to prevent, or rather to protect these organs from injury. So these are basically the functions that lipids perform. Now looking at the structure of a lipid, we did mention already that a lipid will consist of a hydrocarbon chain, a long hydrocarbon chain with a carboxyl group at one end. And then due to the presence of this hydrocarbon chain, which is hydrophobic in nature, and the presence of this carboxyl group, functional group, which is polar, it means hence that a fat acid molecule is amphipathic. It exhibits two properties, and that is it is both polar because of the presence of the carboxyl group, and it is non-polar because of the tail, this hydrocarbon chain. So it is amphipathic. Generally, fat acids can be divided into two. So we have saturated and unsaturated fat acids. And these fat acids are going to differ in their physical properties. So when we look at saturated, the word saturated simply means something is to its maximum, something is to its fullness. So in this case, we are talking about fat acid being saturated. We are describing them in terms of the number of hydrogen atoms. So depending on the number of hydrogen atoms present in a fat acid molecule, it can either be saturated or unsaturated. So a saturated fat acid will consist of the maximum number of hydrogen atoms. It consists of the maximum possible number of hydrogen atoms. That makes that fat acid to be saturated. So an example of a saturated saturated fat acid is palmitic acid. Palmitic acid, which is a 16 carbon fat acid. So it's a very common saturated fat acid. Now we see that fats which are high in saturated fat acids are actually solid at room temperature. They are solid at room temperature. And this has significant implications on the health of the people. It has significant implications on our health. So what's the reason for them to be fats at room temperature? So the reason is due to the van der Waals interaction that exists between the adjacent molecule, the van der Waals interaction. So we find that even if a molecule or substance is electrically neutral, those non-polar molecules can actually develop transient or temporary regions that are going to consist of weak positive charges and also weak negative charges. So those negative molecules can develop temporal. Remember, van der Waals interactions are temporal. They are temporal or transient ionic interactions. So there can be positive and weakly positive and weakly negative charges. Now this occurs because there is a constant motion of the electrons, which causes some regions to have a temporary excess number of electrons and some regions to have a deficit in electrons. So now these opposite charges are going to cause van der Waals interaction between the molecules. Now we understand that the van der Waals interactions are weak interactions. However, they are strong when men occur among long hydrocarbon chains, so they become strong. Now, these van der Waals interactions hence tend to make the substance to be more solid at room temperature, to be more solid by limiting the motion of the molecules. So van der Waals interactions limit the motion of the molecules, and hence we find that these fats that are high in saturated fat acids will be solid at room temperature. When we talk about unsaturated fat acids, remember saturated have the maximum possible number of hydrogen atoms. The unsaturated fat acids do not have the maximum number of hydrogen atoms that are needed. Now this occurs due to the presence of double bonds. Remember, carbon has a valence of 4. Carbon has a valence of 4. And hence the presence of a double bond means that it cannot have another hydrogen atom joined to it because of its valence of 4. So a fat acid will have a double bond between one or more pairs of successive carbon atoms. Hence it is called unsaturated. It does not contain the maximum number of hydrogen atoms possible. So when we look at fat acids, those that have one double bond, we call them monounsaturated, and those with more than one double bond are called polyunsaturated. So most of the naturally occurring unsaturated fat acids exist or have double bonds in the cis configuration. So you have cis and trans configuration. However, most of these unsaturated fat acids are in the cis configuration. So it means that the carbon chain is on the same side before and after the double bond. So this is what we mean when we are saying a cis double bond, same side. So look at the hydrogen atoms. They're on the same side. You have the double bond, the carbon here and the other carbon here. And the hydrogen atoms are on the same side. When we are talking about the trans double bond, the hydrogen atoms are on different sides of the double bond. So this one is on top, this one is the bottom, above and below. So this is a trans, this is a cis double bond, cis double bond. Now, these fat acids that have a high proportion, or rather fats that contain a high proportion of unsaturated fat acid, these tend to be liquid at room temperature. So the reason is just the opposite of what we explained when we said saturated fat acids cause lipids or fats to be solid at room temperature. So that double bond that exists in unsaturated fat acids causes a kink or a bend in the hydrocarbon chain. Now, for the van der Waals interactions to occur, these molecules need to be aligned closely to each other. However, due to the presence of that double bond, there won't be a close and proper alignment. And this will limit the interactions of the van der Waals. And hence, this is going to permit a freer molecular motion. So unsaturated fat acids are going to have a flexible, or rather they are more free to move, and hence they become liquid at room temperature. Okay, so we've already explained that the double bond changes the behavior of a molecule because free rotation does not occur about a carbon-to-carbon double bond as it can occur in the single bonds. Owing to that, we are also saying that fat acids or fats that contain unsaturated fat acids will have a low melting point. So the reason is simply the same, and it is dealing with the van der Waals interaction. Because of that bend at the double bonds prevents these fat molecules from aligning closely with one another, and hence this limits the van der Waals interaction formation. When you look at most of the saturated fats, as we have mentioned, for example, animal fat and those of butter are actually solid at room temperature due to the van der Waals interactions. Now, industrially, hydrogenation can happen. Addition of hydrogen atoms to the unsaturated fat acids can happen. So in the food industry, they apply hydrogenation to make margarine and other foodstuffs. So this leads to the conversion of unsaturated fat acids to saturated fat acid. And hence this makes them to be solid at room temperature. Now, this process leads to the formation of less healthful fats or lipids or foods, because these increase the risk of having heart diseases, cardiovascular diseases in general, which would include diseases that are affecting the heart, diseases that are affecting the blood vessels as well. So this is what the process of hydrogenation does. The other effect that hydrogenation does is that it converts the cis transformation, the cis configuration of the fat acids into trans configuration. So now the trans configuration or the trans fat acids exhibit the same properties as saturated fat acids, and so they also have a great risk of cardiovascular diseases. Now, let's look at the molecule glycerol. We've looked at the fat acids. Now the molecule glycerol. So now this is the structure of glycerol. We said it is a polyalcohol with 3 hydroxyl groups. So 3 OH groups. So 1, 2, and 3. 1, 2, 3. So glycerol has a general formula of C3. There are 3. 1, 2, 3. C3, H8, O3. This is a general molecular formula for glycerol. So we've explained that this is a polyalcohol, which is made of a 3-carbon polyalcohol, and it's the one which is going to combine with fat acid to synthesize a glyceride lipids. And then the physical properties, when you look at glycol or even glycerin, the same glycerin that you use in lotion, it's actually colorless, it's viscous, and also sweet tasting. This is a property of physical property of glycol. So now the presence of these hydroxyl groups will make this substance or this molecule to be water soluble. So it's a water soluble and adsorbent molecule due to the hydroxyl groups that it has. In the industries, this is used as a sweetener, it is used as a solvent, and also as a preservative. And it can also be added in foods, and also in the pharmaceutical or in the drug industries, can also be used there as an additive. And it's also used as a cosmetic in cosmetic products. I'm sure you're very familiar with it being used in the cosmetic industry, for example, in lotion or glycerin, like I mentioned. So this is glycol. This is a molecule, glycol. Now, how is glycol produced? So glycol is actually produced from lipids through a process known as saponification. So lipids reacting with sodium. So for example, we have sodium hydroxide. Sodium hydroxide. Remember, this is a lipid. This is a triglyceride. Triglyceride. So you have the part of the glycol molecule, and you have the part of the the part of the fat acid side. So through the process of saponification, the reaction between sodium and glycerides, what will happen is that glycerol will be produced, and then also the amino, the soap. There will be a production of soap. None of the process is called saponification because it leads to the production of soap. This is how glycerol is produced. This is how glycerol is produced. So what have we talked about? We've talked about fat acids being naturally occurring esters of fat acids. Talked about lipids being naturally occurring esters of fat acids and alcohols, fat acids and alcohols. We've talked about the structure of fat acids. We've said that fat acids contain a long hydrocarbon chain which terminates in a carboxyl group at one end. And hence this makes it to be amphipathic. It exhibits both polar and non-polar properties. It exhibits both hydrophilic and hydrophobic properties. We've talked about that. We've talked about the functions of the lipids. We've said that lipids are very important for storage, are very important for energy storage. We've said that lipids can act as hormones. We've said that they are important for structural support in the membranes, for example, phospholipids, which are part of the molecules that we are going to be looking at in our next session. Also talked about lipids acting as electrical and heat insulators. We've also talked about lipids being used or functioning in the process of buoyancy. Then we've described the fat acids and divided them into unsaturated and saturated. So the saturated will contain the maximum number of hydrogen atoms possible. Saturated fat acids do not contain double bonds. Unsaturated fat acids contain double bonds. And we've said that saturated fat acids will be solid at room temperature, while unsaturated or lipids or fats that contain unsaturated fat acids will be liquid at room temperature. We've described the structure of glycerol, and we've said that it is a polyalcohol. It contains 3 hydroxyl groups, and its chemical formula is C3H8O3, and then it is produced through the process of saponification. Right? Do we have any questions?
Sir,
Guys, any questions?
can you please slow down a bit?
Sorry?
But too fast.
Any question? Okay, so in the next session, those that will be joining us will be continuing. So we're going to look at glycerides, how lipids are actually formed through the process of dehydration, how glycerol and the fat acids are going to react to form the triglycerides, and then we'll look at phospholipids as well, and the other lipids. So see you in the next session, those that will be joining us, and a lovely night to every one of us.
Sir, are you using the same link or you are going to send another one?
For those that will be joining for us, there's another, yeah, it's a different link.
And what time is the next class?
I think your coordinator should communicate when the next class is. It should be maybe between 21:50 or 22. Hey, you have someone who coordinates you, isn't it? Is it Mr.
Okay, thanks.
Yeah, sure.